Hello, everybody. Let's get underway with video 3 of lecture module 5. We're going to move into the terrestrial planets. We're going to start our tour of the solar system in earnest. To start the tour, I want to go ahead and take a look at all of the terrestrial planets gathered up together, plus the moon, so we can see what they look like. And we can see how large they are because all of these images are scaled correctly to size. So let's take a quick look. We are going to start our journey through the solar system with Mercury, which is the smallest of the terrestrial worlds. As you can see, Mercury is only a little bit larger than our moon. Then we have Venus, which is almost identical in size to the Earth. It's only slightly smaller than the Earth. Earth is the largest of the terrestrial worlds. And then we have Mars, which is about half the size of Earth. Bigger than Mercury, significantly bigger than Mercury, but still a overall pretty small planet. So things that you should take away from this, other than, wow, the planets are really cool and beautiful, and I can't wait to learn all about the mysteries of what we've learned about these planets. But things that you might want to know for a quiz or exam, you should know that Mercury is the smallest of the terrestrial planets and that Earth is the largest of the terrestrial planets. All right, so I want to talk about some basics of terrestrial worlds. These are going to be common themes that we're going to talk about for each and every one of these planets. So this is going to be sort of the layout, the outline of how I'm going to address our tour through the solar system. So as we explore Mercury, Venus, and Mars, we're going to talk about their orbital parameters. So what are their orbits like? How circular are their orbits? How far away are they from the sun in astronomical units? What do these planets look like in the sky? How bright are they? How far away from the sun can they appear? All sorts of interesting information about their orbits and how that actually plays out and how we see them in the sky. Of course, we're going to be looking at the interior structures of these planets, as we saw with the Earth and the Moon. Knowing the interior structure is integral to actually understanding how these planets formed and how they've evolved to their current state. We want to look at their surface features and their surface evolution. So how do their surfaces change over time? And what do their surfaces look like? What are the major surface terrains, if we can classify some? What are the smaller scale features? And what are the interesting features that are either unique to this planet that we don't see elsewhere in the solar system, or give us some sort of evidence that helps us understand their formation and their evolution? If a planet has an atmosphere, we are going to talk about it. Out of all the terrestrial planets, the Earth has an atmosphere, Venus has an atmosphere, and Mars has an atmosphere, meaning that Mercury is the only one that doesn't. So we'll ask the question, does it have one? And if yes, what is it like? Can we define the layers of the atmosphere like we did with the Earth? And then we will play another game. How did the atmosphere end up like it is? What is this composition? How did it end up with that composition? How thick is it? Is it most similar to Earth's atmosphere? Is it different than Earth's atmosphere? Is it like what we expect from a secondary atmosphere? Or has something happened to that atmosphere? So lots of good questions, lots of good information about atmospheres, a critical thing that we're going to be talking about in our tour of all the worlds, not just the terrestrial planets, but the gas giant planets, which are almost all atmosphere. And we're going to talk about their near space environment. So near space, so what's nearby it in space? So we'll have to ask the question, does this planet have moons? Out of all the terrestrial worlds, only 2 have moons. The Earth, obviously we got the moon. Hopefully you saw the supermoon recently. It was cloudy. I tried to get pictures of it, but couldn't see it through the clouds. So yes, the Earth has a moon. It graces our skies frequently and has been amazing and delighting humanity for millennia. So the Earth has a moon, but what about the other terrestrial planets? Turns out Mars is the only other planet with moons. It has 2. And then we'll also talk about in the near space environment, things like, does it have a magnetic field? So the big baked potato, small baked potato, is it large enough to drive a planetary dynamo? We have to look at the planet's rotation and its size and whether or not it has a molten core made out of a metal that can conduct electricity and drive the planetary dynamo. And if it does, what can we say about it? Well, I want to go ahead and start by talking about orbits in general. And now that we are actually looking at orbits a little bit more in detail, rather than just going over Kepler's laws and modifying them by Newton, I want to actually talk about some special geometries in orbits. And it's best to actually split the orbits of planets into two different categories. We have what we call the inferior planets and their orbits, and then we have the superior planets and their orbits. This is not a statement of quality. I know that we throw around inferior and superior as statements of quality, but we're going with a older usage of the word, where inferior just means orbits closer to the sun. Superior means farther from the sun. So anytime we say inferior, we're talking about things that are closer. And whenever we say superior, we're talking about things that are further. So our inferior planets, the ones that orbit closer to the sun than Earth, are Mercury and Venus. Our superior planets, the ones that orbit farther away from the sun, are Mars, Jupiter, Saturn, Uranus, and Neptune. So we're starting with Mercury. So I want to start by talking about inferior planet orbits. And I want to define some special points in the orbit, special geometries that are quite useful things and that have helped us actually work out the structure of the solar system historically. There are also things that you can see in the night sky that are remarkable and can be easily noted. So let's start with something called conjunction. And since we're going to talk about inferior planet orbits, I'm going to have the orbit of Earth here. And closer to the sun, here's the orbit of Mercury. Not the real orbit. Mercury has an eccentric orbit, but we'll just consider a circle for now. And we'll start with conjunction. Conjunction is when you have the Earth, the planet, and the sun all in a straight line. So here we have the Earth, here we have the sun, and to put the planet in a straight line, we could either put it right here or right over here. So whenever it's closer to the Earth, we call that inferior conjunction. And when it's farther from the Earth, we call that superior conjunction. So inferior conjunction on this side of the sun, superior conjunction on that side of the sun. Why do we call these arrangements, this geometry between the Earth, the planet, and the sun, a conjunction? Well, imagine you're sitting here on Earth, you're looking out into outer space to observe this planet in the sky. Where would it look like it appears? Well, it would look like it's right next to the sun in the sky. It's along that same line of sight, so it'd be near to the sun. It would look like it's joined with the sun, like they're hanging out together. So we call that a conjunction. And anytime that you have two things that are really close to one another in the sky, where they're not normally that way, we call that a conjunction. We just had a conjunction between Venus and the Pleiades. We're going to have some interesting conjunctions of Venus and the moon coming up as well. Okay, now the more subtle one. Now I'm going to spend most of the time in this video talking about greatest elongation. So greatest elongation is the point where the planet appears to be as far away from the sun as possible. It's going to have the biggest angular separation away from the sun. It's going to be as distant from the sun as it possibly can be in the sky. And for inferior planets, this is always a pretty small number. It's going to be less than 50 degrees for both Mercury and Venus. So if we're going to talk about greatest elongation, we're talking about when this concept of elongation is greatest. So we have to define what elongation is. So I've highlighted that with this yellow, showing this angle right here. So if we draw a line between the sun and the Earth, and then we are going to draw a line of sight to the planet, the angle, so the angular separation between the sun and Mercury, this angle right here is elongation. Greatest elongation is when this angle is as big as it possibly can be. So notice that we can get these greatest elongations where we can make this angle as big as possible. If this is a perfect circular, we'll have one on this side and one on this side. So we have greatest eastern elongation over here and greatest western elongation. Why is this one eastern and this one western? Remember that the Earth is rotating counterclockwise. If we're looking down on the North Pole, the direction that the Earth rotates is east. So this is eastern elongation, and opposite of east is west. So I want to actually dive into that and take a closer look. This is just a nice review. So you can go through the slides to highlight conjunction and the two greatest elongation points. But let's actually look and clear up some misunderstandings and really dive into this elongation. Elongation is a term that is just an angle. It's measured in angles. So arc minutes, arc seconds, degrees. These are pretty big, so we're going to use degrees for this. And it's just the angle between the sun, and the planet. So if Mercury goes around and around and around in its orbit, let's say that Mercury is right here in its orbit, I could draw the angle between my line to the sun and my line to Mercury. And that would be whatever that angle is, say 10 degrees, 5 degrees, that would be the elongation of Mercury when it's here in its orbit. Notice that if this is, say, 5 degrees, we would get an elongation of 5 degrees here, and then another one over here. So we don't really know where Mercury is, but we know that it's 5 degrees away from the, or 5 or 10 degrees away from the sun. So what we want to know is where this angle is going to be the largest. And I'm going to address a common mistake. Most people want to put it here or here, thinking like, oh, well, that is as far, that's the big one. That seems like that would make this elongation angle the largest. But it's not. If you draw a right angle between the sun and the earth, so earth to sun and then straight up, notice that that purple line, there's some orbit out here, so I could actually make the elongation angle larger. You got to wait for the planet to move here to this green line of sight, which lies tangent to Mercury's orbit, and that makes the elongation angle the largest. So greatest elongation occurs here and here, not here and here. So that's why it's a little bit closer to the Earth. And I actually want to see if I can show you this in real time. So here I have the angle, or I have a line between the Earth and the sun, this gray dotted line. Here I have an inferior planet orbit, and this red line is going to be my line of sight. We can go and connect this. This would be conjunction, elongation angle of 0. And as it orbits around, elongation angle is increasing, getting to be larger and larger and larger and larger and larger. Notice it's about to hit its largest where this line lies tangent. And it's a little bit smaller here. So elongation is getting smaller and smaller and smaller, 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 smaller. Back at a conjunction, elongation of 0, getting larger, 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 still getting larger, largest, greatest elongation, smaller, 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 back to conjunction. So hopefully that little visual demonstration helped you realize that greatest elongation happens when this line, the line of sight to the planet, lies tangent to the curve. That makes this angle right here the largest it possibly can be. And now we have superior planets. So now we have the Earth here. So here's Earth's orbit, and this red, call it Mars, is our superior planet, is orbiting farther from the sun. So what kind of special points in the orbit can we define for it? We can still have conjunction where Mars is going to look like it's close to the sun in the sky. So we have the Earth, sun, and then on over here you have Mars. So that would be conjunction, where Mars looks like it's close to the sun, like it's hanging out with the sun, like it's conjoined with the sun. And then we have, as Mars goes around, this would be the point whenever Mars is at its closest approach to the Earth in its orbit. This is also when we'd see Mars go and experience retrograde motion. And notice that now Mars, here we have Earth, we have the sun on this side, and on the opposite side of the Earth, we have Mars. So we call this opposition. And opposition is the point where the planet is physically closest to the Earth. And what would its elongation be? Well, it would be 180 degrees away. It would be the greatest elongation for a superior planet is 180 degrees away. And since it's the closest that it can get to in the Earth in its orbit, it also means that's going to have, that's whenever the planet's going to have its largest angular size and also appear the brightest. And that's all I have for inferior and superior planet orbits. We'll actually pick up with Mercury in the next video. All right, I will see you in the next video.